So today, I want to thank John and Michael for asking me to talk. It was kind of an interesting topic I put together because I've actually been at, like as John was discussing, I started as a DSP engineer and have been at Dolby many years working on a lot of different spatial technology. And noise reduction isn't something that I've deeply spent my career on until rather recently. So I thought it would be really good to have a historical perspective, just kind of look back to some of the early Dolby days. And I'm going to look at some of just the design principles and philosophy and just share a little bit of information about how early noise reduction systems were put together. And then I'm going to fly straight past probably another few decades and end up in machine learning. And then I'll try to tie it all back together again and kind of bring back why I think some of the lessons learned back in those days are still highly relevant today, even though we're using fundamentally different approaches and techniques, and we have far more capabilities and uses of audio than we could ever have imagined 50 years ago. So I'm going to start with talking through what is noise. So let's talk a little bit about what we consider noise. So I'm going to use this definition for the purpose of this talk. Really, it's unwanted. It's unwanted sound that we find unpleasant, something that's loud, something that's disruptive to our hearing and enjoyment of the audio, whether it's for entertainment purposes or for having Zoom meetings over the internet. But really, the unwanted part is the bit that I think really is interesting here, because unwanted is very context dependent. It depends on what the audio system is, and it depends on what the intent of the processing is. We can look at sounds in general. We can look at this eye chart here is a bit of a ontology of one way of classifying sounds in the universe. I don't need to read all the details, but I'm sort of highlighting here that the point is that we can have all sorts of sound that may be, critical to the content that we care about, or it might be considered noise, and it's really content dependent. What I'm showing here is a really neat tool that is based on it's a viewer of the audio set ontology that was put together by Google and a bunch of others that define like an ontology of sounds and sound types, and then they link it to actually a whole bunch of samples. And so you can kind of see that we can classify sounds in lots of different ways. We can call out specific sounds, but it really is dependent on, what we're actually trying to achieve with our audio and what the audio system is about, whether it is a noise or not. So for the purpose of this talk, I'm going to come up with a couple of high-level categories of types of noise and noise that we care about. There's a few different ways you can slice this. This was something that we were doing at work recently when we were looking at what we were targeting. So I'm going to look at stationary noise first. There's probably three main categories of stationary noise that I think are pertinent to consider. Kind of looked at diffuse noise, examples being hisses, tape hisses is what I'll get to in a second, air conditioning noise, HVAC, tonal noise, and I always call out this category of wash. It's a hybrid. It's undulating. It sounds like a wash of noise. It's stuff that's sort of diffuse in nature, but it might have tonal and rhythmic characteristics to it. Then we can go to town when we think about non-stationary noise. I view it as there's a whole class related to speech and speech related degradation. A few examples of this, like my class at noise, are plosives, mouth click, breathing noises, and then we have impact noise. Lots of different noises here, and we can build this list out and create a whole lot of undesirable things that may end up in an audio recording. I've just put a few examples here on the slide, and then we look at the room effect and reverb, and I do put it in the non-stationary category because it's correlated. In some sense, it's correlated to the signal of interest, but you can also see that there's room ambience that I'm talking about here. So there's a element of reverberance that's the sound of the room, but there's sort of early part of reverberance which I think is highly correlated to the signal of interest. So for the purpose of this talk, I'm going to be jumping between these definitions a little bit as I look at a couple of different technologies and approaches over time. Then the next concept I want to talk through is the audio system itself. And there's a number of different ways we can define this. And I'm going to define it for the purpose of this talk in terms of 3 stages. There's a capture stage, there's a transmission stage, and there's a playback stage. And I call this out specifically in the context of noise because we can have noise that is injected or created at any one of these stages. And what it means for our audio system may be different depending on where it's put in. You can also look at this chain and apply it for real-time communications through to kind of content creation and playback. So I'm going to use this to take a step back in time and look at what the transmission stage looked like in the days of tape recordings and analog. So we can hone in on that stage and look at the problem of noise as it related to tapes and film. Now, the predominant concern of the day was tape hiss. It wasn't. It's interesting. I was actually researching this talk a little bit and hearing some of Ray Dolby talk about this from the very beginning. He was actually making the point that in the 60s, studios and recording environments were actually fairly reasonable quality, and it was often let down by some of the tape machines in the studios. And over time, tapes got smaller, and the noise problem with tapes became worse as the signal-to-noise ratio was affected by using smaller tapes and more tracks on the tapes and so on. So tape hiss by far was probably one of the biggest fidelity issues at the time. This is a photo of an early Dolby A unit. It was from the late 60s, probably about 3 years after Ray started Dolby in 1965. You can see on the left-hand side there are 9 what they call Dolby A310 units, and so that big box there was essentially a set of amplifiers and filters and compressors. There was 9 there. 8 were used for the adjacent 8-track 3M recorder. You can see the big tape recorder here on the left, and the 9th one was used for this mastering recording here, where we bounce the master from the multi-track down here. And a lot of recordings that you may know from the 70s were made in the studio. You can see some of the bands there, a lot of Led Zeppelin recordings, and amongst other famous legends of the 70s. So I'm going to talk a little bit about one of the principles around Dolby A, and it's this idea that there's an encode stage and a decode stage, and that when we record on tape, what we're trying to do is remove unwanted noise. So for a loud level signal, right, what we do is we basically push the recording through, and we don't lower the sound. For a low level recording, what we end up doing is we raise the level, and I'll get to the filters and how this looks in the next slide. Record a hotter signal on tape, and then attenuate it on playback. And we use the reverse filters to essentially keep the signal where it was, and the noise drops with the attenuation on the output side. And the filter bank for that looks a bit like this. If anyone's looked at some of the early Dolby stuff, you'll sort of see there's a common characteristic on a lot of these analog systems. There's always the concept of a main path. A main path is essentially where we are not touching the signal, and then this is an encoder, right? So we have an additive set of filters, and you can see it's constructed out of a couple of high pass filters, a band pass filter, and a low pass filter, with a compressor with a compression curve that lifts up low level signals. You can see from that compression curve there, as the signal gets hotter, it's sort of a linear gain. The decode side of this is essentially this in reverse with this system subtracted. Now this is what the gain curve looks like, and I managed to find a manual from 1971 that had a lot of hand-drawn pictures. So throughout this talk, you'll see a lot of pictures that look a bit funny, and that's because I've essentially tried to use the original pictures from either the original papers or the original documents. So this is sort of the range of compression, And it's interesting when you see range of processing adjustments, right? Dolby A is commonly known as an encode-decode system for, reducing tape noise. But what was discovered very early on in the use of it, that it's actually an incredibly useful system for reducing noise in general. So what the product ended up having added to it in later versions of Dolby A, there's actually a control box which consisted of 4 different sliders, which are essentially the gains on each of those filtering compression levels. And so with that level of control, you could actually use this for reducing a lot more noise out of a recording than the tape hits. And it opened us up to looking at HVAC noise, whirring of the camera. That was a very, very common noise in those days, like 35 millimeter film, the mechanical noise. Some of the ambience, and even aspects of wind and other kind of recording issues. Here are a couple of photos. If anyone hasn't seen one of these, this is one of the Dolby A products. Here is the Cat43 expansion module. Kind of interesting design. They kind of have the electronics hanging off the bottom of it where your palm sits. So they kind of had a mouse palm rest back in those days, but that was actually more out of necessity to put the card for the electronics. And so here's a close up from one of the manuals of the Cat43. And so you could control the threshold levels of all compressors in unison, and these are the gains writing into the compressors. What I thought was really interesting in looking at this is back in those days, this was essentially a set of noise reduction presets. So I'm pondering that this is potentially some of the earliest noise reduction presets that exist, because considering this is one of the earliest known mass-used noise reduction systems, and here's a set of presets for the compressor gains, the gains that precede the compressors for wind, camera noise. You can see outdoor traffic noises, close traffic. So it's I think it's sort of fascinating to see that this level, this sort of evolved into allowing film recordings and to use this. It's a far cry from where we've ended up today, right? So this is what this is the state of the art of noise reduction in 2020, right? We're looking at a highly sophisticated suite. It's more than a plugin. It's a highly sophisticated suite that allows an experienced expert audio engineer to do really fascinating and amazing reductions. But Dolby A is still around. If you ever have the hankering to hear it or use it, there's still a bunch of film mixers that use this. So this is actually a Waves plugin called WF43, and you can see it's pretty much a Cat43. All in effect. Another use at that time was there was a sort of this loudness harmonic exciting trick, where you'd take a recording and push it through the encode stage of Dolby A, and then just don't decode it. And what this is basically doing is it's pushing all your HF in a signal-dependent way up through. So it's kind of used in a lot of recordings, and it adds a bit more dynamic punch to it. So this is a plugin called Dopamine that somebody ships today that actually has 2 different things. It's got a Dolby A unit on it combined with a harmonic exciter, and gives a bit more sizzle and airiness to a mix. Okay, so I'm going to talk a bit about Dolby B now. So we're going a bit further into time. So we're looking into the 70s and the 80s. This is clearly the 80s from this image I've used here. And I'll look at the Dolby B system. So this is the diagram of Dolby B from Ray Dolby's paper in 1976 describing the operation of Dolby B. And you can see a similar theme here. We've got an encode network and a decode network. Note here that this is a feed-forward loop and this is a feedback loop. This is going to be significant later when I talk about the digital implementation of this. Each of the networks is identical, right? The only difference is one's an additive booster and one is a subtractor. And the main innovation that they kind of realized at the time was if there was already hot signal, right? Get out of the way. Don't do anything to it. Only apply boost to low-level signals, and that's sort of the basic principle of this variable high-pass filter. Essentially, we put in a signal. It goes for a fixed high pass because there's a fixed attenuation. We essentially, this is the control signal here. So I'm a digital guy. I've done very little analog, but I know when I look at analog circuits, anytime I see a diode, I know that's probably an integrator and a control signal. So you'll see in a lot of these circuits, rectifiers, this is essentially using the output of the effect to drive the cutoff frequency of the filter. Whoops, sorry. And so this is probably one of the early systems where some of the concepts of psychoacoustic masking actually became useful as well, because essentially by moving out of the way with a hot signal, you're essentially masking noise that might be underneath it. So it's really about finding when the signal is low level and applying a boost. So this is what the overall maximum frequency response looks like for Dolby B. So you've got a record high frequency attenuation, and then you've got a record playback. And this filter is a signal dependent filter that will change over time, depending on both the signal level and the frequency of what is being fed in at that time. And again, this is another plot that talks through it from the perspective of putting in a signal at increasingly decreasing levels, and this is the overall system response. So you can see the filtering starting to peak up. This is the shape of the filter, and the filter is moving in frequency and in amplitude as the signal level drops. We jump forward a little bit, and this is actually a diagram that's showing Dolby B as it was sort of documented at probably one of the last Dolby licensee manuals for Dolby B. So this is from a technology manual taken in 2001. It's a fascinating document. It has a 6-page bibliography that teaches the reader of this implementation manual about audio principles and electronics. I don't think we take that much care and attention to things these days, but it's a pretty expansive look at it. And so what you can see here is just a little bit more detail of that first diagram, and you can see sort of an input filtering stage on the encoder. And if you follow the signal down here, you can see the RC network here. That's a filter. It's a low pass filter. It's a high pass filter. Sorry. And then we are, this is the control circuit and the integrator driving the cutoff frequency of the filter here. One of the other common characteristics is a damper to prevent overshoots. Now, on the other side, you can see it's pretty much identical with the subtraction. So a personal connection to this. So when I was working at Lake, one of the things I was doing when I was an early DSP engineer was working on contract for a Japanese semiconductor company who had a series of DSP chips that are targeted at DVD players, home theater and car audio. So it was a full assembly port, a little bit like a Motorola 56K, but with a few extra quirks and a completely different instruction set. I had the fun job of porting and optimizing a Dolby B decoder. And if you think about it, this is an analog circuit, and there's a feedback loop here. So Dolby never actually shipped code for this that was expected to be a working implementation. There was actually code in the kit, but what the code was essentially like a model circuit simulation of it, and highly not intended to be run. And I remember looking at the maths of this and banging my head against, thinking, hang on, there's a feedback loop with no delay. Okay, this is a digitally sampled system. So spent a lot of time thinking, well, maybe we could oversample it. Maybe we could do some mathematical tricks. We looked at Taylor series equations. I spent a lot of time really trying to think about how you would actually build this. And deadlines. As a young engineer, you're hitting up a deadline, and I was like, geez, I'm running out of time to do this phase of the project. What am I going to do? So I turned to our friends at Dolby. So at the time, Lake was an independent company that had a relationship with Dolby. through licensing of Dolby headphone, and I found some people at Dolby who had worked on Dolby B over the years, and there was actually a Motorola 56K implementation, and I thought, wow, how did they do it? And essentially, the way this was actually implemented was the engineer had put a series of probes on the analog circuit and measured voltage levels, and then meticulously built a bunch of lookup tables, and it was simply a bunch of linear interpolators with lookup tables. And I thought, that's really smart. Why didn't I think of that? Not having access to an analog circuit, that was probably one thing, but I thought it was quite a cool approach. So at the time, I was like, no code of this, so I wrote an assembly translator and translated the assembly into my DSP and got the job done. So an example of pragmatic engineering at work. I'm going to jump forward to Dolby SR, right? So there's other whole family of Dolby noise reduction algorithms. They're all just variations on the theme. More gain reduction, more filter stages. Dolby SR was, the piece de la resistance. It was Ray's final big project. He spent 6 years on it. It's a professional noise reduction system that was extremely high quality, and to this day is one of the most revered high quality analog noise reduction processors. Released in 1986. This is the paper that Ray released. I'm not going to go through this in a whole lot of detail. It is essentially building on ideas were in Dolby C. Dolby C added a high stage and a low stage and multiple sliding filters. SR took that even further and put in three a high, low, and a mid stage with fixed filters and sliding filters. It's interesting when I was reading the paper for this, and I'm predominantly a digital person. Starts sounding a lot like the description of a filter bank by the time you actually hear through a filter bank with a bunch of heuristics, when you actually start thinking through the implementation of it all. So I'll share a little bit more. You kind of look at this thing as a wonderful piece of analog electronics. This is an example of one of the modulation stages, and you can tell here we're taking signals in and doing filtering and integrating them. Essentially diodes here are used to integrate them to drive other filtering stages. If we look into one of the signal path stages where the audio flows through, you can see here this is one of the sliding filters. So this is Ray working on it. He actually had a home electronics workshop and squirrel away at home. So you can see him on with a prototype there, and here he is putting a probe on it. Here he is pondering. I wonder what he's thinking there. That's what one of the prototypes looked like close up. And this is one of the circuit boards. There's two circuit boards in the Cat 280. Sorry, this is the 280B circuit board, and you can see all the traces there. 1,200 components were in this. So it's no wonder this was a labor of love and a 6-year journey for him. But one thing I want to take away from the analog set of algorithms is basically this philosophy of the least treatment principle, right? And it's the only do what you need to do to make the signal better. Don't touch it if it doesn't need it. And that's actually the breakthrough moment that inspired Ray to look at what was wrong with earlier tape reduction earlier noise reduction systems. A lot of them were touching all of the signal. A lot of them added distortion to the main signal. And so his aha moment was really saying, leave the signal as it is and only touch the lower parts of it. And we'll see that this kind of principle, I think, is a good one to hold on to, for future algorithms, because we really only want to, from a noise production perspective, we really only want to touch the noise. Right? We want to leave as much of the intended signal intact as we can. Okay, so I'm gonna jump forward in time now. So this next part of the talk, I'm gonna look at the system again, but I'm gonna look at what we learned in speech communication. So this is actually kind of happening in the 80s. So this is happening in parallel to Ray working on his Dolby SR. And we'll look at what was happening in digital audio in the early 80s. And I'm gonna look at noise from the perspective of a speech communication system. So, noise is unwanted sound. So in the context of a speech communication system, we're really trying to reduce everything that isn't speech. And so the broad focus of a speech comm system is to essentially enhance the speech. Often we call it speech enhancement, but we're really trying to get rid of any part of the signal that is not intended. And so if you're thinking of like a common method of the time, was really, okay, we'll walk through this step by step. So basically we take a signal, we take a digital signal, and we do a short-term Fourier transform of the noisy speech. We then have some process that estimates what is the clean speech. Alternatively, you can invert this and say, well, what is the estimate of the dirty part, the noise part of the signal that we don't want to keep? And noise estimation is, the problem to be solved here, right? It's the most difficult one. It's like, how do you accurately predict what is the noise? Very common for many of these systems to basically say, well, amplitude's what you care about most. So we're going to take the amplitude spectrum of what we want to keep, or conversely, what we want to take away, and we'll invert it. Then we're in the digital domain when we throw away the phase information from that, and we use the phase of the original signal, and then we combine them back together again and invert. Right? And if you look at many of the systems for the next 20 years, they're sort of based on this kind of approach. Now, a few things can go wrong with that. One of the issues, obviously, is you're not using the original phase information from the signal, and you can find amplitude differences. Is this a problem? Well, it can be, because when you have finite length segments, you could have frequency dependencies between the finite frames, and you can have overlapping segments, and that's interdependencies. So this sort of represents itself as amplitude distortions. But does it actually matter? Well, the prevailing thought at the time, and this is a pretty seminal paper from 1982, was basically, no, it doesn't really matter. We only have to care about the overall magnitude spectrum. We don't really care about the phase. And here's a couple of tables, and they're doing some experiments with different size digital Fourier transforms. We've got 64.1s, 512.1s, and 436.1s. And their conclusions drawn from this was essentially, as you started turning the phase, you actually get at the right magnitude output. You can see here that they're pretty close. Like for positive SNR, yep, you're good. As you get into negative SNR conditions, it's still pretty good. What they didn't really comment much on is that this is a large transform over here. And if you look at minus 5 dB, what that actually means is that the signal is 5 dB below the noise that we care about. And you're starting to see at big phase shifts, you're starting to see values that don't correlate with what we expect for the signal. So it was starting to show up in those papers, but it was pretty much ignored except for about another paper or two at the time. And for the next 2 decades, and even today, people have really focused on looking at a signal, looking at the magnitude, and then saying that's the prediction. We jump forward to how this has sort of evolved over the next couple of decades. There's a couple of techniques that are commonly used. Spectral subtraction is the simplest one and is commonly used. Essentially, we estimate what the spectrum of the noise is, and then we subtract it. Pretty straightforward. Generally, there's smoothing, and the most difficult part of this is estimating what that noise spectrum is to remove. Wiener filters are common. Wiener filter allows us to have a history. So it's essentially a filter that allows us to look back in time and use historical values in the noise reduction. STSA's, short-time spectral amplitude estimation, is another approach that combines aspects of spectral subtraction, but we actually have a model of the signal of interest as well. So it's actually using information, and we're trying to minimize the mean square error away from a clean speech signal, like towards a clean speech signal. Then we start moving forward a bit more, and we start to have some pretty interesting data-driven approaches. NMF is non-negative matrix factorization, and you can think of this as a classical machine learning technique. We have hidden Markov models, and then we get into the more interesting space of using deep neural nets to predict speech. But before I go there, I'm going to look at what you could do well in DSP, right? So an easier tractable problem to solve is stationary noise, right? We can do predictions of hiss, we can do predictions of AC, hum, electrical buzz. Stationary noises are the mainstay of what we would do with the DSP algorithm. It gets increasingly challenging for non-stationary noises because highly unpredictable, especially impact noises. You have to have an estimate of where that noise is to be able to do something from it. Speech. Obviously, this is highly correlated to the speech itself. And so this is really the domain of, if we look at professional audio and we go back to our toolkit approach, we include a human expert in the loop, and they're driving a lot of very highly sophisticated tools, many of which are signal processing and even machine learning. There's a lot of machine learning driven tools in a tool like this. And so it's a great way to do quite surgical audio restoration. But it's highly labor intensive and requires a human. Even with the ability to automate some of it, it's still incredibly challenging. So this doesn't scale. So I'm going to take one step away from noise for a second, because everything that I was sort of talking about here was we're looking at the problem of communications, right? When I was talking about some of the DSP approaches, and a lot of it simplifies it down to a mono system, right? We look at a mono channel, and we are doing sort of playback and listening of that. But the world isn't mono, the world is spatial. So another kind of really interesting technique to consider is using the spatial information, right? If you downmix a recording or you're only recording in mono, you're not capturing the world, you're not capturing the scene. So how can you exploit the spatial information to do a better job at noise reduction? So one of the ways that you can do that is essentially have a noise reduction system that is aware of the spatial information. This exploits a phenomenon called the cocktail party effect. We're human beings with two ears that live in an auditory system that live in a 3D environment. And so studies have shown that you can actually achieve 6 dB better of noise attenuation through a spatial recording. It's just something that the brain naturally does. They call this the cocktail party effect. And so this is one way to kind of improve the performance of the audio system without, with giving you a 6 dB advantage over what you could do if you just looked at a single channel in isolation. So there may be a few of you on the call that can experience this. So it's just a small plug because we're using a conferencing system that does this. I put a little comment in the chat that if you're actually listening to this on any stereo system that is using one of the applications, you can actually experience this call in spatial audio. And Ross, if you unmute yourself for a second and just say something at the same around me, if you are listening to this in stereo, you will Ross or John, actually, yeah, I can see you on my screenshot. If you just butt in for a second, we can do a quick demo. If anyone's listening right now on one of the systems that support it.
Sure, I'll say something right now.
Okay, and I can say something too. How about we speak at the same time? Ready? 1, 2, 3. Okay.
Now I'll say something at the same time as you, Nick.
Confusing, isn't it? Less confusing than when it's in mono, but yeah. Now that would have worked if you were using one of the dedicated apps. Blue Jeans works with absolutely every endpoint known to man, so it actually goes back to mono for web browsers and other places where they can't carry a stereo signal. Okay, so I'm going to talk about deep learning for a few minutes now. So we'll go back into where things have headed. So one of the sort of the pioneering drivers of noise reduction again is speech communication. It's the thing that's motivating a lot of advancements, especially in the times of COVID. It's amazing to see the progress that's happening in this community, in the academic community over this period of time. With everybody, communicating in the ways that we currently do. Here's an example of one company. This is Babel Labs. who coincidentally were acquired by Cisco today. And they've been looking at, traditional DSP-based approaches to noise reduction. And, really in the last few years, the innovations and the amount of performance using standard subjectively relevant objective metrics has gone through the roof. So the deep learning has really lifted the covers off of what is possible with noise reduction in ways that hasn't been possible. A lot of this innovation is built off the back of what's been happening in the imaging space. And we're kind of at this inflection point, I think, of a lot of interesting things happening with deep learning. So why deep learning? It's a highly flexible framework, right? The possibilities, there's a lot of different possibilities of topologies, structures, approaches, and it's inherently a data-driven activity. So there's a high level of flexibility of how we can actually build systems that can discriminate between speech and noise. We can quickly pull things together, right? With arbitrary inductive biases, we can pull together architectures without a deep understanding of the underlying signal processing. You're really operating in a data-driven world with tools of the machine learning world. We can change the capacity of the model. Like we can scale up the dimensions. We can add bigger data to it. We can add more parameters to a model. It's kind of a scalability that you can't do. That also comes at a cost though, because there's a number of variables that you can play with in all this stuff. So that increases it. But the tooling has come a very long way. There's very efficient tools. Auto grab, back propagation is an algorithm that's makes all this possible. It's calculating through a gradient function the fit of the model. So all these tools make it possible to do amazing things with data. And more importantly, in the context of noise, I was talking about stationary noise and non-stationary noise. Deep learning techniques are incredibly good at looking at how we can do noise reduction for non-stationary noise. So if we go back to our original definition of stationary and non-stationary noise types, we can pretty much target any of these in ways that would have been more challenging to do. Definitely challenging in an analog world, and they're definitely challenging in a DSP world. But we can take that even further. You could imagine and conceive a noise reduction system that is very, very selective, right? We have an incredible ability to discriminate sounds, and so you can conjure up a system that is very specific, that focuses on impact sounds, or focuses on a very, very specific sounds to leave in or take out. So I'm going to talk a little bit about deep learning. I'm going to talk about some common approaches. I'm going to keep this pretty high level. I'm not a deep learning detailed practitioner myself, and so I'm going to approach this from a level of someone using the systems, working with lots of brilliant people that develop these systems, and I'm going to try to pull out some of the salient differences that matter for how the system behaves and what we can achieve with it. So, as I said before, a lot of the deep learning algorithms borrow techniques taken from the imaging world. And so over the last decade, deep learning has transformed imaging and processing of pictures and video. So a very common starting point is to use a deep neural net to take a spectrogram and transform it into another spectrogram. Typically what we would do is we would take our full waveform audio, we would transfer it into some spectrogram representation. It's very common to use a Mel spectrum-based approach like MFCC, but there are other banding approaches. And then we figure out what we want as the desired outcome, and then we use this to drive a set of filters to touch the original audio. Now, I'm going to call this out because this is where a lot of the audio-based systems have been focusing on. And it's suffering from some of the same problems that we looked at in the 80s with throwing away phase, right? So a lot of tricks are actually done to either preserve the original phase, match the original phase, or process the original phase so that we can reconstruct a full waveform of audio later. A lot of interesting innovations are sort of happening around how this sort of mask, we call it like an image mask, it's an audio mask, might get applied to the audio. And we can also construct networks where phases are treated as images. It's a more complicated thing to do because phase, if you look at any phase images, it looks like a bunch of white noise. So another approach is to say, okay, we're going to convert our audio into a frequency, a Mel spectrogram. We're going to have a network, and we're going to train the network and build the architecture in a way that we can output direct waveform audio. And the way this is typically done is with a vocoder, right? These are often generative networks, and they're networks that have been trained to know how to create a specific type of audio. So speech, you might train one on speech, and it knows how to fit speech. So a lot of the innovation in this space actually comes from text-to-speech machine learning algorithms, where we put in a text input and we're getting clean waveforms out. And so a lot of those principles and ideas can be borrowed to take a very noisy signal that looks something like speech, and if the model is only trained to create speech, it's going to put out clean speech. The problem with these kind of models, though, is because we're very far away from Ray's principle of do no harm. If it isn't touched, it's broken. We're completely generative speech. So these models can go wrong by flipping phonemes around and doing some weird things with speech. And so you have to ask the question: is it better to have noise leak through, or fundamentally modify the meaning of what comes out with the speech? So it's a challenge with that kind of generative approach. And then where the current state of the art is really pushing is models that map inputs that are audio and audio, waveform audio at the output. Now, these models end up learning transforms. So they kind of end up learning transforms inside them that do some kind of frequency-related clustering of speech. It's very predominant in some of the early layers of these networks. And so there's a lot of work going on in this space at the moment. So I'm going to then talk about a couple of other common architectures that you may come across when people are describing machine learning systems. So the first one I'll talk about is a recurrent neural net. Okay, so an RNN is essentially, it's a feed-forward network of connections, and it has state backwards, so it can actually retain a little bit of state. RNNs are typically used for speech-related NLP systems, right? So they're very good at remembering sequences of things, language translation, or turning speech into text. So an RNN is a pretty good network of that because it has the ability to have delayed memory, which is really useful when you're looking at the relationships between sound over time. They're also interesting in that they can be built in a way with very little look ahead. So a lot of the real-time systems that are using deep learning for noise reduction today that want to have very low latency without having to see much of the signal use an RNN approach. They're often combined with this notion of a thing called an LSTM, which is a long-term, short-term model, which gives extra state within itself. Now I'll contrast that with and sorry, I should point out that this is our little time window at the top here. So we have a slice in time, and there's a little bit of memory in the model. This is causal, so I'm assuming I put a little bit of delay into it to get that there. Another very commonly used architecture is a convolutional neural net, and these are used very, very frequently in the imaging space. You can see here we've got like a window of interest. So in both of these examples, I'm using a MagSpec MFCC spectrogram representation to show, and then this is like the window of interest of the network. And these arrows are signifying that as we move the audio through the network, we're shifting that box around as inputs. And so a convolutional net, it's not technically convolution in terms of the signal processing sense. It's a sliding dot product, so it's very close to a convolution. And we end up doing a lot of layers feeding into a model that sort of folds the data down in different permutations. And then there's a neural net inside, and then it deconvolves it on the way back out and expands it back out again. Another approach is called a GAN, and these are really interesting approaches. So it's called a generative adversarial network, and so what I've shown here is that they're used quite often for systems that generate something out of nothing or something out of a feed. So this is an image that was fed into a GAN that has creatively created something out of nothing. And it looks a bit like they've, So GANs are typically used if we want to synthesize speech or create something. And so the way I kind of look at a GAN and how it's different to a CNN and an RNN is you actually build GANs out of CNN networks. But the main difference is that when you are training a model, right, you're trying to optimize for reducing error differences. So you generally have like what they call a loss function. And so in a CNN standard network on its own, the loss function is fixed, and every iteration of this back propagation algorithm is trying to do like a minimum error reduction to converge on a particular result. GANs completely change that, and instead of having a fixed function to compute the error as it's doing as it's learning, you actually have two models. You have a discriminator model and then the main model, and they feed off each other. So the training process is actually dynamic. Okay, now I'm gonna put these up here. I'm not gonna do a deep dive. I wanted to give you all a bit of a flavor of where we're at in 2020, and one of the reasons I'm bringing up some of these papers is just to show you like how machine learning models tend to be thought of, and you'll see their combinations thereof of different operations. So this is a paper, a recent paper, and it's a CNN-based speech enhancement, aka noise reduction, and this is the primary model on the right, and you kind of see here we have a whole bunch of convolutional layers, and they shrink over time, and then we basically have layers in the middle, which are essentially the machine learning aspect of it, where there is a nonlinear function, right, which is actually the smallest divisible thing of a neural net. And it's one way to think about it. It's a connected system where it's what they call an autoencoder. So you have information coming in, right? This was probably audio at some stage, but it's been permuted into a vector of numbers, and it's folded and twisted and folded and twisted, and there's still information in that representation. And it's connected to the output layer. So each of the input layers is connected. We reduce the data down, and then we expand it back out again, and there's mathematical connections between every state of it. That's an example of what a CNN looks like. This is a very hybrid example. So this is another paper that is what they call hi-fi GAN. So it's a generative system, and it's combining actually concepts of a CNN. It's combining concepts of a GAN style model, right? So we feed waveforms into it. We have a whole lot of data redundant folding as we do the dilation layers, and then we have these discriminators, which are actually CNNs of themselves, and then we have another CNN which is looking at it. Some of these are looking at it in terms of the original audio, and then some of it are looking at it in terms of frequencies, which is the MEL spectrum. This model is pretty interesting in that you can see it's combining a lot of techniques, and it's producing very high quality waveform audio on the output side. This is another approach. And this is what they call a dense unit. So it's another autoencoder structure like the first one I showed you, with a technique that's commonly found in a recursive neural net. So this is a long-term, short-term kind of set of filters essentially with nonlinear functions, nonlinear mathematical functions that allow the inner layers of the model to have state over time. And this model here is like one of the sort of state of the art in single channel speech noise reduction. And lost my control. This is yet another model. So this is a convolutional neural net, and this is operating on waveform in and waveform out, and it's essentially using a source separator. So some of the models actually will apply masks such that you can reduce noise. This one actually, it's possible to create two separate signals. So these are often related to some of the models that are used in music source separation. And so what we're actually doing is we're doing a separation of the noise signal. Sorry, I should restate that. We have learned the model, so we separate the speech signal. And then we do subtraction of the noise part. And finally, I'm going to show you one other topology, and this one is again really hot off the press. So there's a conference called Interspeech that is held every year, and they publish a paper with a set of data sets and criteria, and everybody bakes off their single channel speech enhancement algorithm. It has a real-time part of it, so there's a real-time competition and a non-real-time competition. So this is a paper that was published this month of a net called PocoNet by a team at Amazon that won the non-real-time part of it. And it's combining a lot of different ideas. Positional embeddings is a way of kind of having orthogonal mathematical representations of characteristics of the sound. It is going through an STF-FT, and it's another model that's based on this sort of dense UNet approach. Now, I wasn't going through that a lot of detail. If you are interested, I put some links here of all the papers. It's worth taking a look if you find this interesting. I put a couple of links of some places to look at if you just want to learn a little bit more about deep learning. The first couple, this is a good reference site. This is a good course. And this one's a bit audio focused by a researcher called Jordi Pons, who's part of the Dolby team in Barcelona, and he publishes a lot of training material. So by all means, take a look at that. I can paste this in the chat window later if anyone wants a real-time copy of any of these links. And these are links to sort of all the papers that I was talking about there. So I'm going to come back to, noise being unwanted sound. So while we have a lot of networks and topologies and ways of reducing sound, there's a lot of different people trying different things at the moment. To reduce noise. There's a lot of variation in approaches. And then I guess the challenge is, if we're looking for a good result, what do we use? I feel that in just sort of general audio processing, right, you may use one of these models for a specific function. And the real, I think, opportunity and challenge here is how do we orchestrate a set of algorithms to achieve a desirable result for improving audio. We can also layer machine learning on top of that to help classify what is in the audio. We can use machine learning to help decide what processing to use and how much of it to use and in what configuration. We can even look at the video to help augment decisions that we make on the audio. But I think the biggest challenge that we're going to find with all of this is it's really highly dependent on the audio system itself and how we want to interact with it. Ideally, this would be automated, but what would an interface look like? So I'm going to come back to coming back to the original Cat43 noise reduction unit. What was simple about this is there are 5 sliders and you have 5 fingers, right? Somebody could build a tacit physical knowledge of how moving their fingers could adjust the sound. This is incredibly difficult in a machine learning world or a world with highly complicated algorithms. So one of the things we're doing is we're looking at how do we provide processing as a service, and how would we present this to an end user? And so this is like a queuing interface. This is an idea for a queuing interface that essentially it's a hybrid. It gives a little bit of user control to signal to intent, like what you actually want to get done, but a lot of the complexity of what algorithms to use and how much is sort of handled as using a set of heuristics and machine learning to make the right decisions. So closing in this talk, I zoomed. I went from noise reduction all the way to machine learning like that. The main reason I did that flyover is it's another world, and it's been another world to me. And I've been learning machine learning, relatively recently. Having done my career as a digital signal processing person, I'm fascinated in the progress. In my own company 5 years ago, we had an early machine learning team. We were using classical machine learning techniques for quite some time. I've used them in a lot of products for essentially setting parameters and classifying things, right? You can take a data set. You can say, I want optimal behavior in this way, and you can train it. What's really fascinating is with deep learning, we've gone to a place where it's more of a data-driven thing, and a lot of the techniques are machine learning concepts. They're not audio concepts. that drive a lot of the innovation. So it's a really interesting time to be kind of in this world. But if I was going to take away, if I wanted you to take away one thing from this talk, it's really, I think, a fundamental principle. It's like we call this, recently I was calling this in my team, do no harm, right? Do no harm to the process, only process what you need. And I don't know whether it's just being through osmosis of being at Dolby for 16 years. But when I actually looked up, I'm like, hang on, that's the original Dolby A principles. It's the principle of noise reduction, do no harm to the signal. But I think a lot of the art of making a good system for noise reduction is how you abide by that principle in the system and in the algorithms. Through the talk, I did touch on a few DSP, one aspect of DSP. I didn't deep dive in that, but I really wanted to kind of focus that mono-channel speech performance is a key part of what has been driving a lot of signal processing in that space, especially as it relates to noise. And then I kind of stepped through some of the deep learning areas. So all I want you to take away from this is really think about, what is unwanted. Like when we talk about noise, what do we actually mean? What do we want to leave in the signal? What is unwanted noise? What is the signal we want to preserve? Context is very important. The intent of the end result is a really big factor in this. So, with the state of the art of deep learning, we've proven that we can, use lots of different approaches. When we look at a high quality noise reduction system, it invariably involves a mix of techniques and a mix of ideas, a mix of things put together in an optimal way. And the key to success here is being able to provide it in an easy to use way. And most importantly, from the 60s onwards, let's make sure whenever we're looking at these systems, we look out for systems that do no harm to audio that we don't want harmed, because I think that's a fundamental principle to be taken away. So thank you.